get going. Now, it's my longtime habit in running these boot camps to use the first part of each day for a bit of a retrospective on the previous day. Sometimes this emphasizes key points. Sometimes this brings out additional components that I neglected or put in the background the previous day. So yesterday we had a pretty full day. We started, after a bit of orientation, we started by looking at an initial model, which was buzzing, gloom, and confusion, I'm sure, to many of you. We had a model which depicted a GIS, a context which was situated spatially. It used GIS information to actually place resources like grocery stores, convenience stores, etc. And we had individuals circulating in that context, securing food from different sources and being influenced by the distances to those sources, convenience stores, grocery stores, and also being influenced by the placement of parks as well for recreational opportunities. And we saw how the model, that model with which we started, it included within it a description of several interacting processes. Some of these processes were processes involving mobility, people's movement to particular locations that were selling food in various forms. Other aspects of the behavior of the model related to individual decision making about what food they would consume for a given meal. Yet other components, processes, had to do with the people's weight change over time, as influenced by their food intake, to be sure, but also as influenced by their physical activity. So this model was in a situated context, and people circulated, and it captured the set of interacting processes. Now we're going to be building that model, or a very close variant of it, in another day or two. But what I hope that model brought out was a view of dynamic modeling as consisting of the depiction of one or more populations over time as they evolve, and the way in which it captured mechanistic processes that are operating at the level of particular causal pathways playing out. So rather than purely dealing with observables, purely dealing with quantities that are directly empirically measurable, it tends to involve additional factors that are what statisticians would call latent. They lie underneath often observables, but they're involved in dynamics that are often quite important for shaping the evolution of the system. Following an observation of that model, which also served as a way to kind of understand how some empirical data could come in, GIS data, data related to the nutrient density of certain types of meals, the placement of food sources, etc. We then went on to discuss, in a more broad level, the enterprise of system science. And I noted here that when we're dealing with external systems, often those systems confront us not only with in the sense of being complicated, but in the sense of being complex. They have, yes, many moving parts perhaps, but more to the point, they incorporate certain features such that the whole is greater than the sum of the parts, or it's different than the sum of the parts. So they exhibit features such as delays, nonlinearities, feedbacks. They incorporate complex network structures. They incorporate aspects of spatial context and components in many areas of nonlinearity that combine to mean that if we want to understand the behavior of the system, we have to look beyond an understanding of the individual components of the system or pieces of the system. Surely those pieces are extremely important for the behavior of the whole, but beyond that, there's a set of processes that give rise to very different behavior at the level of the entire system than you observe in any one piece of it. And I gave the analogy of a traffic jam, that the behaviors we see with a traffic jam, the dynamics we see with a traffic jam, are not merely immediately reducible to the obvious components, the cars that are sitting in that road, the number of axles that they have, and the size of their tires, and the size of their engines. Surely those things are somehow involved causally in this traffic jam. After all, if a car breaks down, and it may contribute to that traffic jam. But they are the issues with the traffic jam. Its timing, how long it lasts, when it tends to form, involves a lot of other factors besides that. And I argued that while we're very good traditionally in science at breaking things down into the pieces and studying them, whether it's through very carefully designed biologic experiments on our lab benches, or whether it's through carefully controlled, randomized controlled trials, we're very good at understanding in a very detailed way the behavior of pieces. But we've traditionally been less good at putting all those pieces together to understand how they influence the whole. And system science aspires to be that science of the whole. And one of the key tools in the system science toolbox is dynamic modeling. Perhaps it's the most important tool. Dynamic models, I noted, characterize the state of the system at a given time, and then simulate over time, mimic over time, the behavior of that system as it progresses through sets of states. And in that sense, they mimic features in the world that we're interested in better understanding. But system science models in general, and dynamic models in particular, are not merely sort of simplified attempts to depict the structure of the world. That's much of their function. But in other ways, they serve as thinking tools that help us go beyond merely musing about theories for how the world might be operating in our head, and allow them to capture them in a computer, a computational form, where we can do several things. We can share them with other people, we can collectively critique them, and we can refine them over time based on those critiques. But perhaps most importantly, ladies and gentlemen, we can, by having them on the computer, we can ask what's their logical consequences in terms of behavior over time. If we have a theory that's merely in our head, it's hard for us to consistently think through what the implications of that are. We're just not very good in terms of our thinking capacity to be totally consistent in our understanding of how a system will evolve over time. In fact, there's some fascinating studies that have been done by John Sterman at MIT and others looking at giving highly technical, very well-trained graduates these are graduate students in fact, within the science, technology, engineering, and mathematics areas, and giving them very, very simple problems involving simulation to think through in their heads. And they've documented huge discrepancies between what those individuals come up with and the actual behavior of those systems. And what it goes to show is that even if we're highly trained at a conceptual level in certain types of mathematics, we're not very good about reasoning it through consistently in our heads. We need help, and the help here is computational. The help here is turning to a computer that will do what computers are best at, which is they'll do a tremendous amount of dumb computation. Dumb, but intricate. So they can simulate out for us the implications of a theory as captured in a model in an unambiguous way, and tell us what the implications are for system-wide behavior of that depiction. Now, by so doing, that doesn't guarantee that this theory, this dynamic hypothesis captured in a model, is correct. Far from it. But it helps us more quickly identify discrepancies between what this theory implies and actual empirical data. It helps us identify what would normally be latent or hidden misunderstandings or discrepancies between what we think might be going on in the world and what we actually observe. It helps us, in short, spot errors in our thinking, spot errors in our conceptualization more quickly by comparing them against empirical evidence. And we saw that a model like this, as we run it, we can observe behavior both in the small, the behavior of particular agents, and behavior in the large. We can see, as we run a model, data from across the model regarding patterns. Say the number of people with diabetes over time here, the number of people overweight, the correlation coefficient between being overweight and being diabetic. We can compute any number of statistics about a model like this, and for some of those statistics we may have real-world analogs to which we can compare the model, and we may find discrepancies between what the model depicts and what is reported from the world. And that can clue us into ways we can improve the model, and sometimes it clues us into problems with the data from the world. I've been in a number of situations where that's been the case. So models here serve as learning tools. Jeff, currently out in the hallway, speaks about them as learning prostheses. I didn't fully appreciate this until I broke my foot last year and sprained an ankle. And the idea here is that just like a prosthetic, like a crutch or like a cane can help us, or like a big boot, can help us overcome certain limitations, to function despite limitations. They help us function more naturally, help us get around. So it is with models. Models help overcome our limitations in thinking in our heads and sharing understanding and understanding the logical implications of our theorizing, and they help us take that theorizing and make it operational in a way that we can understand its implications far better than we could in an unassisted way. So learning prostheses is, I think, one of the best ways to refer to models. They help us overcome our limitations and function better by dealing with by complementing our shortcomings, and let us do what we do best, which includes reasoning about possible theories that might explain patterns, recognizing patterns in large amounts of data, etc. So I talked about models as learning tools, and this is not a universally held perspective within system science. This is not a universally held belief even among dynamic modelers. But it's one that I think is pretty compelling from a scientific perspective. Okay, following that, and at lunch, we jumped into building our first models. Actually, we went through a couple models, and after lunch, we built some of our own. And the first model that we built up was a model where we captured heterogeneity in a population. We introduced some characteristics, a person's location, a person's sex. We gave them a visual representation, and we captured income. Notably, we made some of their characteristics, namely income, dependent on other characteristics, namely sex. So we saw that we could capture not just each characteristic of the person as being drawn from some independent distributions, but instead we could capture interactions between those factors, cases where income may be linked to education and sex, or perhaps income is related to age and sex, etc. And this was a point that isn't immediately obvious to people within any logic, but is readily doable. We also saw how we could impose on the model empirical distributions. Any logic includes a rich support for models that include random variables, that include uncertain factors. And some of those factors involve static quantities that we had yesterday, like sex and income. And we could draw values for those quantities from predefined distributions parametric distributions, or we could define them from, or we could draw them from empirical distributions, such as we might capture through a custom distribution object in AnyLogic. We also saw that a model capturing this sort of heterogeneity can often be visualized very fruitfully with a variety of mechanisms. And we saw how we could change people's color and their size and their placement to encode certain aspects of their situation or behavior, etc. Okay, so that was our first model, but that model lacked a key spark, a key feature associated with it. And that is, it lacked the ability to reason about behavior over time. There were no dynamics in that model. It was a static model, a model that had no change over time associated with it. In fact, it flew in the face of what we were seeking from a dynamic model. So in the second part of the afternoon, we introduced dynamics in that model using a construct. And that construct was state charts. And we saw that within these models, while they're certainly not the only mechanism for depicting evolution of state over time, they're a very powerful one. A state chart simultaneously captures, all in one, several different features. So a state chart characterizes, with respect to a particular concern, such as someone's diabetes status, a set of possible states, often categorical in character, most traditionally categorical in character, that they can be in. And with respect to that concern, these states are collectively exhaustive and mutually exclusive. In short, you're in one state or another state with respect to this diagram. Now, I'm going to break down that fiction a little bit in coming days. We're going to have hierarchical states, where you can have one state that includes several others. But when it comes to these simple states, you're either in one or you're in the other, and they describe collectively all the possible states you could be in with respect to diabetes. But we could have different state charts for different concerns. So here we have some states associated with our weight, and here states associated with diabetes. And at any one time, we have a single status with respect to diabetes and a single status with respect to weight. So we might be obese and diabetic, or we might be normal glycemic and overweight, for example. So we can be we're in one particular state with respect to this first state chart and one particular state with respect to the second state chart. So one of the things that these state charts capture, ladies and gentlemen, are the possible states you could be in with respect to different particular concerns. A second thing that these state charts capture, ladies and gentlemen, is actions that change your state. And those actions are depicted here using these arrows, these transitions. So the fact that we have an arrow, for example, from normal and underweight to overweight indicates that you can become overweight having been normal and underweight, right? Or you can become diabetic, being now normal glycemic. So the arrows, the transitions, indicate actions that can change state, things that modify your state, which is, after all, the name of the game here. We're building a dynamic model, and for a model to be dynamic, to be changing over time, it has to have some way of changing the state. And so these transitions, these arrows, provide a way to capture that. A second thing that those arrows capture, though, very importantly, the structure of those arrows, their connectivity. They capture the context, the rules, the conditions under which those actions take place. So the fact that we had, for example, the most basic feature of this is we have an arrow from normal glycemic to overweight. And one of the things that indicates is you can only travel across this arrow if you are currently normal and underweight. If you're currently in a different state, say overweight, you're not eligible to make this transition. It's only if you're in this state. That's one thing. But then we saw that if we actually went into the arrows itself, to the transitions itself, there was further detail. And each type of these transitions had a specific type of semantics, type of meaning associated with it, type of logic associated with it, type of rule. So this is a rate transition, ladies and gentlemen. This is specifying a hazard rate. And this hazard rate is 1 divided by 40 numeric terms. So 0.25% per year. That's a hazard rate. It's a probability density, a chance per year that you'll go, but it's a per year chance. It's not actually just merely a probability. It's a probability per year. And the average time in that state, therefore, since this is the only transition out, the average time in that state is the reciprocal of this, which is 40 years. Okay? So we could associate transitions with hazard rates. And in fact, those hazard rates could change over time. They could even change based on how long you've been in this state, which is notable. Particularly compared to, Markov modeling where it would be a fixed probability. It could also depend on other features going on in the model, perhaps something about the policy context, something about the structure of the built environment around you. That could affect this rate. So just because we have a fixed number here doesn't mean it's limited to that. And then I introduced another type of transition early on. In fact, we started with that type of transition. Does anyone remember what that type of transition was? Other than the rate, what was the other type we saw yesterday? Yeah, it's a timeout. And a timeout transition, so a rate transition, if this is a fixed time, a fixed rate here, it is what we call memoryless from a stochastic processes or statistical context. In other words, no matter how long you've been in this state, if you are there now, then you have the same chance per year of leaving it. You may have just come in, and over the next year you'll have this probability per year of leaving. Or you may have been there 10 years already. In fact, 50 years already, you still have the same chance of leaving. You have the same kick of the can no matter how long you've been there with a fixed rate here. So it's what we call memoryless. It doesn't matter how long you've been there, you have the same chance to leave. By contrast, a timeout transition, ladies and gentlemen, is the exact opposite. Here, we might have the same average time in that state. Maybe I'll make an average time of 40 years. But this is the exact opposite of memoryless. This is totally memory full. It depends. It's not. The other one, it didn't care how long you've been there, you have the same chance of leaving. Here, it depends entirely on how long you've been there. You aren't leaving until you've been there for exactly 40 years. And then you will leave. And that's it. Game over. So those two are sort of polar opposites. Timeout, it's the opposite of memoryless. It depends exactly, it's dictated exactly by how long you've been there. You will leave after exactly that amount of time. A memoryless transition, a rate transition with a fixed rate, it doesn't matter how long you've been, you have the same chance per unit time of leaving. So you can think of those as polar opposites. They might have the same mean amount of time that you spend there, but they are very different consequences. And when we ran the model, we saw those consequences writ large. And if I may, here we go. We'll change it back to a rate transition. The mean time in this state will be 40 years, and I will run it. And what we will see in terms of people's weight status is changes over time, where some people developing overweight earlier, some people later. Next, let's try making this a timeout transition with the same mean time. And we will try running it, and we will see a very picture. So right now, there is no overweight in the population. Then suddenly, at a certain time, there's a complete overweight. So let me try that again. I will restore this. Remember our use of this method too. Remember, we could set it to run as fast as possible this way. We could slow it down here. We could speed it up. I'm going to slow it down, start it running, and then I'll speed it up just a little bit, okay? And we're going to see it, boom. Suddenly people become overweight all at once. They all go down here. It's no chance about the matter. They're going to go. That's totally deterministic. The rate transition is stochastic. It certain chance each time you come in here, you have a certain chance per unit time of leaving during that period of time. Okay. And as Joe asked yesterday, if we had gone down to look at the level of a particular person here, there's actually a little counter. I didn't really emphasize this much, but you'll notice there's this little counter that says for them they will become overweight in 64 years. Okay, this one in 54 years. This one in 2 years. One, boom, he's about to become overweight. Boom. Okay, became overweight. So this counter indicates how soon you will leave.
No,
Yes.
counter.
Yes.
Is there a number on population 0? Does it start counting at 0?
I'm sorry. So that number indicates how soon you will be leaving the state.
There at 0. Yeah.
Sorry? Oh yeah, there's a number at 0. That's because here we'll see how we can watch that. So give me just a second. So here's time 0, and we'll go to a particular person. This person will become overweight in 71 years from now.
The question is just that
Yeah.
is it the zero indexed array? The
Oh.
zero indexed array instead of a one indexed.
Yeah,
That's
yeah.
the question.
Oh, is that it?
Yeah, sorry.
Oh.
Obviously not a computer science.
Okay,
I
sorry.
had to get used to that.
Sorry, I thought you were talking about this number, but you said this number existed at time 0?
Going at 0 at the
Person is 0.
Person.
Oh, person 0. Yes, we. So this is a gap between mathematicians and computer scientists.
Yes.
Of some note. And computer scientists start counting things at 0, and mathematicians start counting things at 1. And it leads to a certain discontinuity when there are students who cross the border. But yeah, this starts at 0. So the first person in the population, somewhat confusingly, is given index 0. And if there are 10,000 people in the population, you will find, or 1,000 people in the population, they are numbered 0 through 999, right? If there's 2 people in the population, they're 0 and 1. If there's 100, it's 0 through 99. If there's 1,000, it's 0 through 999. Yeah. So those of us who circulate back and forth between math and computer science have mixed minds about which is the best convention. But this is one, and it's consistent. It works pretty well. And it's sure nice to have both zeros and ones to work with. Yeah.
So agent 0 in 2 states at the same time?
So we'll be clear here. So each of these state charts, it's a great question, and I welcome it. And your name? Muhammad. So these 2 state charts, each of them depicts a person's state with respect to a specific particular type of concern. So this state chart captures a person's state with respect to diabetes. This state chart captures their state with respect to their weight. Okay? Now, these states within a given state chart, these sort of simplest states, the smallest level states, these are collectively exhaustive and mutually exclusive. You're going to be in exactly one of these at any one time, okay? And they depict all possible states you could be in. So you've been in exactly one with respect to for that particular concern. But these represent different concerns about the person. So you're never going to be in 2 states at once here of these simple most states. But you can be, and in fact you will be, in a particular state with respect to each of the state charts, because they represent different considerations about types of considerations about this person. They represent different different concerns. So these ones involve my weight. These ones involve diabetes. There might be another one which has to do with my employment profile. Whether I'm currently unemployed or in school or full-time employed or part-time employed. There might be another one with respect to my my attitude with respect to care seeking. So I'm seeking care, or I'm not seeking care. There might be another with respect to my TB status. In fact, with respect to diabetes, so I might be, susceptible to TB and a latent state of infection with respect to TB, or I've developed active TB in an uninfectious state or in an infectious state. So we might have many state charts for a given person, and each depicts a separate set of concerns. And with respect to a given concern, say, wait, you're in exactly one state at a given time. Is that helpful?
Yes, thank you.
So it's not really that the person is in, we could say at a colloquial level they're in two different states, but that's going to be misleading. It's going to be an ambiguous statement. It's not that they are in two different states in a conceptual sense. They are in a particular state which is characterized both by some aspect of what their situation is with respect to diabetes and what their situation is with respect to weight. So this person is normal and underweight and normal glycemic. Another person might be obese and diabetic. That's at the same time. So those are just different, their state with respect to different considerations. Is that helpful?
Yes, thank you.
Okay, very good. Any other questions about that? Yes, Roberto.
If the person is aging,
Yes.
when, for example, it turns from 39 to 40,
Yes.
the risk of diabetes will increase regardless of the obesity level. Is that correct? So how these two play, how
Yes.
do they interact?
Yes, so it's a great segue. That's the first thing we're going to be doing. Putting in place aging and capturing aging-related risk in some of these transitions. Okay,
But
so
aging is a combination between timeout and
no, well, there's several ways to capture it. At a general level, we will often capture it in a way that aligns with biostatistical characterization, in the form that we will have hazard rates that are dictated by a set of coefficients. Some of which will take into account age, others which will take into account different risk factors like weight, others of which might take into account some aspects of their surrounding environment. And so, like I'm not sure how familiar you are with competing risks analysis or survival analysis, but often there we'll use Cox proportional hazards analysis or some other technique to characterize this hazard rate as some factor involving odds ratios and so on. And so we might represent it as, so we'll write x as e to the some beta 0 plus beta 1 times some weight. If we imagine weight as a continuous variable, plus some beta 2 times age, plus some beta 3 times aspects of their history of weight, so weight history plus their cumulative obesity dose or what have you. And so this would be a type of analysis that could come out of Cox proportional hazards analysis, and very closely related to one from accelerated failure time analyses. And the point is that that often that's a convenient way to characterize hazard rates, these hazard rates within a model. And so often our models in this context will incorporate equations like this as for these rates here. So instead of having a fixed rate here, I will have an equation that involves some beta terms and covariates being considered, and I'll just plug that in directly here. And so one of the terms would be age, and we'll see how that can be incorporated in just a minute. Another term might be their current weight, another might be their past weight, another might be their smoking status, the redundant variable associated with smoking, if they're a current smoker or not. And I plug that in I plug that in for the rate associated with that. And then as those other factors evolve, as they stop smoking and as they lose weight, it would lower their hazard rate associated with this. Does that make sense? And that's a very straightforward thing to do in here, and it's one that's well supported by a lot of the research that might go on to estimate parameters for a model like this. And many of the models that I've included for you, probably, I don't know, about 10 of them or so, include exactly that for their characterizations of hazard rates. Okay? Is that a question?
Yes, if the hazard rate cannot be, if you want to use more complicated models, that
Yes.
is not one of the default models.
Okay.
Is it possible to?
Yeah, yes, it is. Great question. Terrific question here. And your name again?
Joanna?
Joanna. Yeah, so yes, it is. And we saw some of that yesterday. There's several layers of understanding here. So one thing we noted yesterday is that the timeout, well, it's most commonly used in the context of with the toy models that you'll see from me online and so on. You'll see it often with a fixed timeout. In general, we can draw a timeout from distributions, and we might, if we have a more sophisticated model for how the timing of this transition, we might draw this from a custom distribution that we define not as a fixed quantity, but as one that depends on other circumstances of their situation. So in general, we could call off to some function that computes the timeout to use, the time that they should leave. And that function could be a very complex probabilistic model about when they'll leave. By the same token, if you want to deal in terms of hazard rates, you could compute the hazard rate not in this sort of fixed way, but based on a more sophisticated model. And an example of that would be an accelerated failure time model, which actually does include an additional term or two. But in general, we could use these built-in types like timeout, like a rate transition, to put in place mechanisms for more sophisticated characterization biostatistically of the timing or the hazard rate that applies. It turns out that it's more general than that yet, in the sense that you can also use certain conditions, and as we'll see soon, probably under Krugerian influence, we'll see how messages can be used to dictate the timing of their transition. So that it doesn't even have to be the case that we have to give a formula for when it will occur or with what probability density it occurs. Instead, we could send a message, go now, if we wanted to use that sort of mechanism. So it turns out these transitions, they may look simplistic at first, but actually they're collectively, if you consider all the different triggering conditions, they're very powerful. They're very powerful. Hope that's of help. Any other questions? Remember, I view answering questions as the most important thing I can do here. So, okay. So anyway, we introduced state charts, and we saw yesterday we could use state charts to characterize some very important interaction between state charts. The fact that we have multiple state charts here allows us to parcel out the possible state a person could be in into multiple pieces in a fairly neat way. We don't have to consider simultaneously all possible combinations of this, which would get quite overwhelming if we start to think about additional comorbidities. If we start to think about additional factors like their employment status or their type of profession or what have you. And we had many state charts. If we had to consider all their possible combinations combinatorially, it would get very messy. And indeed, that's what you deal with highly stratified aggregate models. But the fact that we can characterize these things as different state charts lends us an economy of expression of a person's elements of a person's state. But it does not require them to be independent. So yesterday we captured a measure of coupling or dependence between these two. So when a person was in a certain weight state, we imposed a certain risk of becoming diabetic. And what this captured is the fact that we have with different weights, we have different risks obtaining in terms of the chance of becoming diabetic on a per year basis. So while they were in the normal and underweight state, there was one hazard rate that applied for going here. When they were in the overweight state, another hazard rate applied here. When they were in the obese state, yet another rate applied. Okay? Now, the generalization of this is, in fact, this guy here. And related to Joanna's question, we needn't, Joanna, have this be beta 1 times some indication of weight. We could just have essentially dummy variables where, there's some component from weight that is different for this and this and this. So essentially it's like having beta times a dummy term, are you or not normal and underweight, another beta times a different dummy term, are you or not overweight, are you or not obese. That's what we've kind of got here. And this developing diabetes hazard was a variable. And I was asked yesterday, what's the difference between a parameter and a variable? A parameter encodes assumptions and communicates those assumptions from the point of creation to the thing that holds the parameter. So if there's a parameter in person, that the assumptions about that parameter are communicated from the population in which the person is located to that individual person. So they are told here what to assume for their parameter. And I'll just go open that model yesterday. Here we go. And that first model, you'll recall that we had a population in Maine, and this population, it specified values for the parameters for each person. Each person here had a sex and had an income, and the values to assume for a particular person were specified by the population that created them. So the population would say, hey, okay, you're going to be created, you should have a sex drawn from this distribution, and you should have an income as dictated by this formula. That was a parameter. If a parameter lived in Maine, what was it that dictated the value of that parameter? Does anyone remember? The experiment. The experiment dictated it, indeed. So this was in Maine, and so when we had a large population, we could use 100,000, medium population 50,000, and we don't have to futz with modifying the model at all. We don't have to modify the model in the least. We just run the model with this alternative assumption. And why can we do that? Because it is a parameter in Maine. Okay? Okay. By contrast, ladies and gentlemen, variables were used within our models to capture quantities that changed over time. And I spy 3 of those here. And 2 of them had to do with the visualization and are more epiphenomenal. They're just kind of cluing us into what size to depict this as, the circle, and what color. But beyond that, we had this variable here that every time someone changed the state, it would be set as well. And every time someone changed diabetes status, this color variable will be set. Every time they change these status, these variables will be set. So variables allow us, ladies and gentlemen, to change the underlying state in response to say, changes in state charts or other types of changes. They're a way of keeping track of additional state, and in this case, the hazard rate that obtains. Okay? This wasn't the only way of capturing interaction between state charts. There's many other ways, but it's one of the more easy to understand, elegant, scalable ways. So we saw how we could use variables for that, and we saw how they were distinguished from parameters. There's nothing that tells this variable initially what it should be in the population that creates this. Instead, we set, associated with this variable, an initial value for it, and after that it was the same. Someone asked me yesterday, why did I just set this to 0 initial value? Well, it was because as soon as we come into the state, when you enter a state chart, you come in here and you immediately go to the first state. And in this case, it directly overwrote visual size here, directly wrote over developing diabetes hazard combination. So I was kind of, I didn't really pay much attention to what I entered here because I knew it would be immediately overwritten. Okay, so those are some reflections in the models yesterday, some loose ends that I wanted to tie up, some points that I wanted to emphasize. Any questions before we go on to new material? Yes?
Can we just go over this item and
Sure.
sell, yes.
Sure.
And also, can we have a list of them?
Yes. I will commit myself
It's like
in my fine TAs to creating a systematic list that will accompany the documentation that I've already provided to you on the site, namely the handy reference sheets. So we will supplement that. We'll fortify it with the discussion of these issues, okay? Looks like the TAs may be picking straws as to who does it.
I'm just checking if we already have the notes on that.
Okay. So let me briefly recap it. Of those, if we had to put those in context, if we had to compare their significance, this, self, this item and self, I place in that order. This is far more important than the others. The term this, it's pervasive throughout any logic models for a very good reason, because it comes from Java. Okay, it's the base. Any logic is built on top of this language called Java. Okay, the language called Java was invented, about 20 years ago. I remember it well. My TAs do not remember it as well. It's a cross-platform language that has been used for many types of software and serves as the basis for much of today's computing infrastructure. Any logic is built atop of that language. So this stuff that you see here is Java code, okay? It's code written in the programming language Java. Now, the programming language Java uses the term to describe when you have code, that code is running almost without exception. Almost without exception, it's running in a certain context of a certain object. In this case, don't worry about objects too much. It's in the context of certain agents or main, okay? So code within any logic, this sort of code, like in entry actions or exit actions, or code as we'll see in events, or code that's associated with transitions, that code is running in a certain thing. But it's as simple as this. If you, okay, no pun intended. So if you take a look at code here, you just have to look to see what's open now, and you see this is in person, okay? So this code is always going to be running in the context of a given person. Some person is coming into this normal and underweight state here, okay? There's some particular person coming in here. There's some particular person here who is becoming diabetic, okay, right here. When that person enters there, they are becoming diabetic, okay? And it's a person, it's in person, so we know this is occurring in the context of a person. A person is becoming diabetic, a person is becoming overweight. Now, who is that person? Who is that person? We want to often know, who am I? Maybe we want to log ourselves to a database. We want to say, I became diabetic today, right? Maybe we want to record something about the cumulative number of diabetes years in the population. Maybe we want to record the cumulative number of obesity years in the population. Whatever it is, we often need to know, who am I? Okay, I'm becoming red, but who am I? I am this. That's who I am. I'm this. I'm the current person. That's what's called this. And if we saw code in main, And unfortunately, this model is bereft of it, I think. But if there were code in main here, there we go. There she blows. You didn't know, that's a bit of Java code too. This is referring to main. It's referring to current thing here in main. And I have you put this in just to be consistent. It's going to help you avoid certain problems if you're explicit about having this. So this is referring to me, whoever is currently executing. This is inside of main, and therefore it's me. It's referring to main here. And in this case, we've only seen it so far as this dot. Soon enough, we'll see it more than that. Before this morning is out, as long as you don't run out of the room, you will see this used in additional ways that will make sense. So this refers to the current thing that's executed. Now, I detest having to say that. That makes me feel terrible to have to say it, but that's sort of my way of explaining it. So this code is executing in the middle of something, and it's executing in the context of main. This other code is executing always in the context of some particular person, and you can refer to that person by saying this, okay? That is the person. So you could log their name to the database by logging this dot name. You could log, the number of times I've become infected as this dot infection count and put it in the database. We could print out, when I get infected, I could print out, this to report who got infected. So it's kind of my name for myself. Does that make sense? Okay, that's the hardest part, okay? That's the hardest one. That's the universal one. That's the ubiquitous one. It's the one I wish I didn't have to tell you about. Although the others qualify too. Okay, so let's go talk about the others. Okay, the others are fictions, are artifacts of any logic, are vagaries of any logic. They're okay. So here's the deal. Here's the deal. Let's go to this one build. Okay. Here we go. Boom, boom, boom. So here's the first model we built. And for this model, we wanted to set the, okay, so I am getting confused here. Let me go look at main here, yes. And no, the problem is that, okay, I'm confused. Okay, I thought, sorry, I was in the wrong model here. I thought this is the first model. Okay, fine. So here we go. This is the first model we built. Here we had, we were saying, what should we assume for the sex and income? In short, the parameters for each person in this population. Each person in this population, you may remember, had a sex and an income. And what the population, since it contains people, it's responsible for creating those people. It's responsible for telling those people what to assume about their parameter values. They have parameters, the people in this population, and it's a job of population to tell them what the values of those parameters are. So if you had a population of Sydney and a population of Melbourne, they would have slightly different characteristics. The population of Adelaide, population of Adelaide, is eating floaters would be true. And population of Melbourne, has nice river would be true or whatever. So they would have certain values for the parameters. Okay, so the population is going to tell the people in the population. Each person is going to be told what to assume for its parameters. There's two parameters here: sex and income. So it's going to tell them what to assume for sex, what to assume for income. Each time a person is created, it's going to run this, and it's going to run this to determine their sex, run this to determine their income. Okay? Now, if there's interactions between them, like income depends on sex, it's only then that we need the self thing. It's only then that we need it, because we need to be able to refer for the same person who's being set up, whose parameters are being dictated. Now one parameter depends on another. So we need a way for the value of this parameter to refer to the value we already set for this person who is being set up. what is their sex? And so we say self.sex. Now that's just an artifact of how any logic tried to provide a way so you could refer in later parameters to earlier ones. And you refer to it through self. Now why don't you use this.sex? Because this is main. As I told you, to figure out what this refers to, you just look up here. You just look up here. If I'm in main, this refers to main. It's like, this population size. That's mine. So it's main. But main is doing the job of setting up this person, their sex, their income, etc. And so we need a way. We can't say self.sex. That would mean like, what's main sex? And main doesn't have a sex. So instead, self.sex is referring to the person who is being set up, whose parameters are being set up here. And that's basically that's the main place that you'll see that. Okay, now you will see it one other place, and there's a good chance that you will see it today in one other place. And that is a place involving discrete event modeling where it refers to the current block. So the block will be appearing, so the block might be, get me a nurse. And it's occurring in the context of a clinic class, in a clinic. So there'll be person here as an agent, there'll be a clinic agent. So this block's appearing in the clinic. And so this refers to the clinic, but I want to refer to the block, to the thing that says, get me a nurse. And so I'll refer to that with self. Yes, Dylan.
So I've got 2 points to make on this. So first, even though we're having large discussions about this, I'll point out that it's not a common thing you need to worry about when you're actually constructing these models. You might have to do it once or twice to get something set up, and then after that, you don't have to think about it very much. And second, when in doubt, you can just use autocomplete. Because when you're using autocomplete to say either this or self, it will tell you what the type of that is. So if you use this and it says main, you might think, oh, I've got to use self. If you use self and it says it's the discrete event block that you're in, then obviously use this or an agent. So I think that's kind of 2 valid points, I think. Maybe the first one is not so valid if you're doing certain types of modeling, but I rarely come across the
I rarely use
self
it too.
This.
I rarely use it too.
Yeah,
and
but for the purposes of these exercises, it comes up a lot when we're showing you the different things.
That's right, and partly it's because, for many years my boot camps were free of this stain of using it. But then people start to ask me very recently, how do I make one thing depend on another? And I thought, gosh, there's lots of documentation how to do just that sort of thing. But if you want to make them depend on each other, people are lost about how to do that. So I thought I'd tell them. But then that introduces this whole worry. But this is not that common.
Yeah.
It's not that common. That is not that common. Yes?
So if you use the wrong one, does the model still compile?
No, it'll be unhappy. You want to see what will happen? Watch this.
And if you use the wrong one, autocomplete won't work.
Watch this.
It won't give you what you're looking for.
Okay, so...
Unless the droids are looking.
Quite right. Well spoken. Okay, so if you do this, it'll say sex cannot be resolved. So it'd say, oh, maybe I need item. Watch this. Maybe I need item. Never need item. Item cannot be resolved. Guess it must be self. Okay, now it's a happy camper. No, I don't suggest doing that, but it actually works as a technique, a process of elimination. I want to get on to item, though, and then I'll come back to you, Dylan.
Oh, okay. Well, can I just it's going to take about 10 seconds.
Okay.
I'm just going to point out that even those of us who know what we're doing will sometimes do this if we forget which one to use. It's just like, it'll take you a total of 7 seconds to go through those 3 options if you can't remember. And one of the 3 will eventually work. So don't overthink it. When in doubt, bang your head against the problem until something happens right. Until something works.
Well, yeah. Banging is maybe too strong an analogy. So my wife is an MD PhD, and she is from toxicology background. She got her PhD in toxicology, and she was taken aback by seeing how I experiment with programs, and let's try to see if this works. Let's see if that works. Try this. And in chemistry, that's not something you do. As she told me, a person who was doing something incorrectly in our lab caused mustard gas to form, and they had to evacuate the lab. And so you don't just say, "What the heck? Let's try this." And this comes out importantly in our differences about cooking style too. She told me that I can resume my cooking once I get a second kitchen because I am rather more free in my combination of the ingredients. But when it comes to this, there's no hurt in experimentation. There's no hurt in experimentation. It can be very readily done. Now, where is item? Item is used, to the best of my knowledge, in one particular context. I only know of one place. Does any of the TAs know of any other? It's used in statistics.
I think probably.
I think, yeah. I can't think of anything. Maybe there's...
When you move your mouse, though, do you see that little bulb beside?
Yeah, this at least tells you, use item. See, but it says it in a somewhat inscrutable fashion. It might as well be Russian. Use item, the embedded object. And it's not clear in what sense it's embedded.
But it's clear you don't use self.
Yeah, you don't use self, and it's not inviting you to use this. Item is referring to the current thing about which you're computing the statistics. You're computing the statistics over a population, and for each thing in the population in turn, it's going to call it item. It's going to call it item, it's going to extract something to take the statistic over, but first it's going to test, is this condition true, if you provided a condition. And if so, it will consider that, and it'll apply the metric to that, and it'll go on, and apply the statistic to it, it'll go on to the next, calling each of them item. That's where that's used. I've never seen self used there. It's very rare. You very rarely use this there. I can imagine cases where you would, but it would be very rare. But almost always you use item to get at most. I mean, if you use this, you'd use item in one place and this in another component. If item.income is greater than this.income threshold, you might use that for the condition or something. But item is referring to the thing over which you're taking the statistics. Is that helpful? Okay. So item is only used for statistics, to the best of my knowledge. Self is used in very rare circumstances when you need parameters of an agent to refer to one another, and then occasionally discrete event modeling. This is used many places to refer to the current thing.
Can I just ask one other question?
Yeah.
So
This is great.
I had trouble, my code completely wouldn't compile, and it turned out that it was missing a this dot, right?
It was what?
It was missing this,
Yeah.
right? It was missing a this dot. Because I hadn't put it in at all. Like, it's all, like, I know that you said it belongs in, like it refers to the piece of code that you're writing, but you don't put this dot in front of every command, okay, when you want to write in that, to that sentence. So like, yes, I get what it refers to, but I still am not sure about when you would put it in.
Well,
Like, you don't write it in, if you go to the thing where this dot is, you don't put it in every command you've got there.
you can put it in for most things. There's going to be rare cases where you don't put it in. Like this should really be this dot sex distribution. That should have been there. Okay, like this dot log normal.
Log normal doesn't belong to the name.
It does yeah, it does. Log normal. Yeah. It's in use normal. So you actually could do it more or less for most things. There are some cases where you're asking something instead of main, you're asking about you're asking instead of for the current object, you're asking something else to do it. But it's pretty standard that it's used for most things. But yeah, I'll certainly grant there's some exceptions to it, because the whole point is there's certain things you ask from the current thing and there's certain things you ask from elsewhere, and that's what this is this it just making it clear, you're asking the current thing for this information versus something else. And that's why we say this. Using this consistently, I'll admit that I sometimes lapse in terms of that, but it helps students avoid certain mistakes. Kurt.
Maybe a good rule of thumb in that regard is to use this anytime you're referring to something you've created. So you create a statistic, you create a parameter, you create a value, you create a state charge. And the reason why is because like human languages are interesting because some languages don't have the prepositions attached to them, they sort of imply. You just say, you say mine, you don't say that's mine, you just say mine. So human languages have these sort of applied things. Computer languages have a hard time with implications in that way. So Java wants to know, like, you can name something, you can create a parameter, and you can name that parameter. The same thing in main is you can create another parameter called sex, if you want, within person. Both of them can be named the same way. And the way you separate which one you're using is by sort of attaching on the ownership of that thing. So the this dot or the person.
John's dog versus my dog.
Yeah, so if you're in main and you want to access something in person, you can say, person dot whatever. Like you get the name of the person, you say person dot whatever. So the dot is like an apostrophe s, right? And so in Java, all you because it's very particular and very precise, because of that requirement for precision, you have to always be clear whose parameter name you're using. So that's the only reason why you would use this. So it's probably a good practice. Sorry?
Is it wrong? Because that's exactly what I do.
So if you don't actually have to, this is often implied. So you don't technically need to use it, but it's really good practice to use this anytime you're using something that you've created.
So in my boot camps, about half my boot camps I teach without using this except when necessary, and about half that I did. And that continued to a boot camp Kurt was at in Minnesota in February, where there was a bug caused by not being careful with it. And I just decided, okay, after that I'm always going to use this. Just going to use it as a standard thing. And it'll prevent people from getting, lower the chance of a bug.
It's a question of style.
Yeah.
Yeah, so like, do you put, if you have a list of 3 items, do you put commas in between all 3 items even when you have the word and? I mean, in English, you can sort of make that decision. So it's just a style guide. So we would suggest that because we've been burned by it before, you just use, anytime you're referencing like a noun, a thing that you've created, put this in front, just to verify. I think we can do it.
Yeah.
Yeah, that's a good.
Yeah. Yeah. Okay. Any other questions right now? You'll see more about this. You'll see it a few more times. You'll see this a few more times. Okay. Okay. Great. Okay. We're exhibiting video dysfunction now. So, wow. Look at that. Look at that, Dylan. Wow. Okay. So